Richard, please.
Okay, thank you. So what is a little unusual here is this is the outline of my talk, and you see the first item here is where I try to explain what the title of the talk means. So we need to know, well, what is the Hausdorff dimension? What are iterated function systems? And I'm also going to talk about something called contracting similarities. Try to give some examples of simple cases when you can compute the Hausdorff dimension. And those will be this middle third Cantor set. I'll remind you what that is and how there's a theorem about how you compute that. You can do it exactly. And this Koch snowflake is one of these. Once I show you the picture, you'll recognize it, one of these fractal sets. And then I want to talk about two examples where you can't do it by some nice theorem. You need to actually do some numerical computation. And that is what are called continued fraction Cantor sets. They're easy to define. I'm going to define those for you. And then, so those are going to be one-dimensional problems. And then the second thing is iterated function system generated by complex continued fractions. So that'll be a two-dimensional problem. Okay, so there are a lot of definitions of dimension. Before I started working on this, I thought dimension was like, 1, 2, or 3. They were always integers, that was it. Of course, there are definitions of dimension that aren't necessarily integers. And let me just mention one that's a lot easier to talk about than the Hausdorff dimension, something called the box dimension. So that is a definition of the box dimension. It's pretty, n of epsilon is the number of boxes of side epsilon required to cover your set. And then you take this limit, and the limit is the box dimension. And as I said up there, it coincides with the usual dimension in simple cases. So if I just had the unit square, well, how many boxes would I have? I would have 1 over epsilon squared. So I take the log of 1 over epsilon squared over the log of 1 epsilon, and I get 2. And you'll be happy to know that that would be the dimension of a square. Okay, but you could also get something that was not necessarily an integer. Okay, then we come to the problem here is the Hausdorff dimension. Well, the Hausdorff dimension is it's complicated to define. I'm going to define it. However, I will say I'm never going to use this definition of the Hausdorff dimension in the rest of my talk. So it's a complicated thing. As it says here, you have your set in Rn. You take this countable collection of delta covers, so the width of the sets are delta. You take the infimum over all possible things to the s power. That's something with two parameters, s and delta, the diameter. You can define a Hausdorff measure. You take delta going to 0. And then you can finally get the Hausdorff dimension. According to this formula, you look at the infimum of all these hs of f, set of s to give you 0. To me, this is not at all intuitive. So I don't have a lot to explain, but you see this comes up when you have fractal sets. You want to be able to measure them in some way, and this is commonly used. Okay, so the next thing in my title are what are iterated function systems? Okay, well I have a bunch of mappings, theta 1 up to theta m, defined on some closed subset in Rn. I'm going to start off talking about the case where these are affine maps. That's the simple case. That's not the case of the computations I'm going to do, but that's a case in which you can actually compute precisely the Hausdorff dimension. So if these are affine maps, then I call them contracting similarities. If I look at this norm and they're just equal to some constant times x minus y, Ri would be, if they're contracting, would be less than 1. Okay, if you have this particular setup, and you have a finite number of the maps, then it turns out there's a non-empty closed bounded subset K and D. This is called the invariant set associated to the iterated function system, such that K is the union of everything you get when you take the maps applied to K. So that's where invariant. And what you want to do is compute the Hausdorff dimension of sets like this. Okay, still a little too vague. Let's get down to an example here. So what about you want to compute the Hausdorff dimension of the middle third Cantor set? What is that set? You start out with 0, 1. You take out the middle third interval. Then you take out the middle third interval again. You keep doing that according to this formula. And if you remember the Cantor set, it's an uncountable set. It has Lebesgue measure 0. And I want to compute its Hausdorff dimension. Now the way we can do this, it turns out that you can get this set by two contracting maps. Very simple. X over 3, 2/3 plus x over 3. These are contracting similarities. It's easy to check. The r's are 1/3. The set C that I'm going to be talking about is going to be the set of all the limit points where I concatenate these maps. So I have the two maps, theta 1, theta 2. I take all the compositions of these maps. I look at the limit points. There's a theorem, not new to me, but there's a theorem. When you have this situation, contracting similarities, they satisfy some open set condition. I won't define it. It's a technical condition. Ri is the ratio of the similarities. K is the invariant set. Then it turns out that the Hausdorff dimension of K can be S, and S is computed by this very simple formula. So what would it be in this case? Well, R1 and R2 are a third. I solved the equation 2, 1/3 to the S is 1, and I found out that the Hausdorff dimension of this middle thirds Cantor set is the log 2 over log 3. Okay, then we have this famous snowflake. So what do? You start with an equilateral triangle, say on the left. If you look at the, let's say, the bottom line of the equilateral triangle, you divide that line into 3 pieces. You take the middle piece and you draw these line segments to form a triangle down there, and then you take away the line that was the part of the line connecting that triangle. You do it everywhere, and then you keep doing it, and you get this fractal set. And then you'd like to know what is the Hausdorff dimension of this fractal set. Okay, it's not obvious, but it turns out that you can generate this particular snowflake with 4 maps. And these 4 maps are all contracting similarities. And you can calculate the ratio. According to my formula, they're all a third. So you have to solve this 4 to the 1/3 S is 1, and you can easily solve that, and you find out that the Hausdorff dimension is the log of 4 of the log of 3. Of course, you have to convince yourself that those are the maps that generate this particular snowflake. Okay, so those are things people know, they're simple, but what happens if you get something you don't know how to compute? So I want to concentrate in one dimension on what are called continued fraction Cantor sets. So there's 2 ways you can represent real numbers. You can just take an infinite decimal expansion, or you can take a continued fraction expansion. So that just means you've given your x, say between 0 and 1, and you write it as a continued fraction, and all these are integers, a1, a2, and so forth. Every rational number is going to have a finite continued fraction expansion. And now people in number theory are interested in the question, well, suppose I restrict the a's in the continued fraction expansion to specific values. So their ai's could be m1 up to mp. And then I want to compute the Hausdorff dimension of everything I get, all these numbers. Okay, so the simplest case is this E12. So that means, what are all the continued fractions I could get? What are all the numbers I could get if I only allow the a sub n's to be 1 or 2? Turns out I get some Cantor set. It's in this interval. It has 0 Lebesgue measure. And then the idea is it can be related to these maps. So I can generate this set by getting 2 maps, and there they are. They're not affine maps. They're more complicated, but they're not too complicated. And just as in the other case, I can write this set E12 is all the limit points I get if I concatenate all these maps where M1 or M2 is either 1 or 2. So I want to compute the Hausdorff dimension of the set I get. Okay, I can't do it by the formula. Okay, so now we come to the combination of functional analysis and numerical analysis. The first thing is the functional analysis, and this is why I say I won't use the other definition of Hausdorff dimension. It turns out that for a long time it's known there's something, a transfer operator, it's called in various contexts. It's a Perron-Frobenius operator, and you give the sets theta, and you form this operator, which depends on the parameter s. So the s appears in that superscript. And now there's a theorem. So we like in numerical analysis, before we apply a numerical method, we like to have what is the theoretical background. And the theoretical background is, for every positive s, this operator has unique, with scalar multiple, strictly positive eigenfunction, Vs. So, and the eigenvalue for this function is the spectral radius. The mapping from S into this eigenvalue is strictly decreasing, it's continuous. And here's the thing, you can estimate, you can bound all the derivatives, the pth derivative v sub s, simply by a given constant, only depends on p and s times the original function. Very unusual, not something we see in PDEs too much, but we have it here. That's one of the key properties. The second key property is you can relate two neighboring points. So if you have this eigenfunction, v sub x2 is bounded by v sub x1 times this exponential, completely determined. And then here's the thing in the theory, that the Hausdorff dimension generated from these maps is the unique value of s such that the eigenvalue lambda s is 1. Okay, so for every s you get some eigenvalues, and you want to know when is the maximum eigenvalue 1. Okay, so now I would like to approximate this. And you could say, this has been a conference a little bit on compatible discretizations, so I'd like to show you where compatibility enters here. So this is very simple. I'm on 0, 1, I take a uniform mesh, and then I approximate a function by a continuous piecewise linear interpolant. So that's what it is. Everybody's seen that before, and we know what the error looks like. The error is these distances times the second derivative at some intermediate point. So I'd like to just use this in order to get some information. Okay, well, if I take, so if you look at this mapping, I have to evaluate a function at some point, theta mj of x. Well, I'm not sure which subinterval it is in, so I have to figure out where it is. If it's in that subinterval, then that's its interpolant. Now I use my theorem. How big can Vs double prime at that point be? Well, the theorem says it's just bounded by some constant times its value over there. Now I apply my interpolation error estimate. The difference between the interpolant at that point and the function at that point is bounded by this guy times the second derivative at some intermediate point, but second derivatives are bounded by this thing over here times Vs at theta mj of x. I don't know where that is, but it can't be any bigger than the maximum. So nothing too tricky here. However, I also have a second thing. Not only are the derivatives bounded, but any two points are related by that inequality. So even though I don't know what the maximum is, they can't be any farther away from the mesh point xr or xr plus 1 than this quantity. Okay, so I know I have that, and so I can take a convex combination, and I can get this. So when all is said and done, I put all these things together, and I find out the difference between these two things is bounded by something in terms of the interpolant itself. Okay, so now I claim that I have precise upper and lower bounds on the error that only depends on the function values of the eigenfunction at the mesh points. So I define this thing I call the error. It's all explicit. I have for every mesh point, xk, that lies in that interval, I know that the true eigenfunction at that point is bounded by the interpolant at that point, and the lower bound is the interpolant with some small error. Okay, so my goal in all this is to not only define a numerical method, but I want to do something that's we can't always do in PDE. I want to give, so I compute an approximation to the Hausdorff dimension. I want to give explicit upper and lower bounds so that I actually know, it's not some error like some constant I don't know times h to a power times the bound on some derivative I don't know. I want numbers, so I want to give explicit estimates. Okay, so how am I going to do that? Well, I look at the equation for the eigenvector and the eigenvalue. So the eigenvalue I'm seeking is the spectral radius times the eigenfunction is the operator. There's the operator, but I just know something about v sub s. It's bounded by this guy over here above and below by that guy. Okay, so now I define two matrices, the upper matrix and the lower matrix. And basically, I can associate with every xk, v sub x of xk is some vector, wsk. So I'm taking these points, I'm getting a vector. I define a matrix, like you see up there. And basically what I'm saying is that indeed this is my interpolant. And here's the key thing. These matrices have non-negative entries for h sufficiently small. So I started off with a positive operator, and what I want is, I want matrices, positive matrices. That is, they're all matrices, all of whose entries are non-negative. Why do I want that? Because I need a compatible discretization. I need something that has this property. Okay, then I have this key lemma. I guess, you know a lot about linear algebra. I've never seen this lemma before. So if I have these results, it says that the spectral radius, wsk, is bounded above and below by these guys. And here's the key lemma. You give me a n by n matrix that has non-negative entries, and here's the key thing. You have a vector with strictly positive components. Then if you have these upper and lower bounds for that vector alone, then you have upper and lower bounds on the spectral radius of that matrix. And that's what we're going to use. So if I have that estimate up there, and I have this lemma, this says that I can bound the spectral radius of the matrix LS, which is exactly what I want to compute, by the spectral radius of these two eigenvalue matrices that I know explicitly. So I just have to compute the eigenvalue, the maximum eigenvalue of these matrices, and those, I'll show you how, give me the bounds I want. Okay, so then one more fact. So what's the Hausdorff dimension? The Hausdorff dimension is the value of the parameter s, they call it s star, for which the spectral radius of L sub s is 1. Okay, if I could find a number s1 so that the spectral radius of my matrix B is less than 1, then I have this inequality because the mapping is decreasing from s to lambda s. If I can find a number s2 such that R of A of s2 is bigger than 1, then similarly I have a lower bound on R of s2, R of s star. So the idea is if I take a fine enough mesh, I could make these differences small, and I will get very good upper and lower bounds for the spectral radius, which is the Hausdorff dimension. So what do I have to do this? Well, I have to solve a nonlinear equation. Namely, that the spectral, I have to find an S such that the maximum eigenvalue of AS is 1 and the maximum eigenvalue of BS is 1. Okay, so you give me an S, I have to plug in, I want to find the maximum eigenvalue, I can just go to MATLAB or whatever, use eigs, and I come out with that thing. Of course, this is a function of S, and it turns out that this mapping from S to the log of RB sub S is convex. So instead of solving that problem for the spectral radius, I solve log of RB sub S is 0. And this is a convex, so this converges very rapidly, this nonlinear equation. I can even use the secant method or anything I want. And then, of course, to get the other one, well, they're pretty close, so I have a good starting guess. Okay, so I do this. And I get, since a lot of these have been computed by other people to a lot of accuracy, then I can compute the errors. And I see this is done just MATLAB, single precision. Those are the mesh sizes I'm using. I think you're seeing H-square convergence, which not surprising given you're using linear elements. Okay, so then being a finite element guy, it's natural to say, yeah, well, why don't you use higher order approximation? Well, here's the trouble. You don't maintain this property of positivity. Because you know that if you have a linear function and it's non-negative at 2 points, non-negative everywhere in between. If you have a quadratic function, it's non-negative at interpolation points, it's not non-negative everywhere in between. So you can't do that. Okay, but currently I'm working with my colleague Roger Nussbaum. And it turns out that he's a guy who spent his whole life worrying about mapping cones into cones. And there's a lot, so we're using something we call hidden positivity. So you could say that this mapping I have, it maps the usual cone, non-negative functions into non-negative functions. But that's not the only possible cone in the world. So we have come up with other cones where we preserve this positivity in that sense, and then using it to prove error estimates for higher order piecewise polynomials. To see why you'd want to do that, well, I just did some trivial computations. I tried to keep, well, I did. I kept the number of unknowns constant. So if I increase the degree, I increase the h. And you can see, even with that, I'm certainly getting very good approximation as I increase the degree of the polynomial. Of course, you have to be careful. We're seeing that when we do this with smaller h, you know, you have Runge's phenomena, so we're kind of doing interpolation. You can't have interpolating at the mesh points. You have to use some kind of piecewise Chebyshev points to make sure things are not getting out of hand. So you would do interpolation at different places. Okay, now a lot of the people who work in this assume, you know, everything's analytic, and that's what their theory is. But we want to show that really we're not doing that. We don't really need all this continuity. And we could do an example where we didn't have all this continuity and everything would be fine. So we just concocted some example of mappings that map the unit interval to themselves. There are C3 mappings. They're not C4 mappings. When lambda is 0, I just get this Cantor set where I know the answer. I can still compute for this example explicit bounds on the derivatives. We do computations, and everything works just as in the other case. Okay, so I'd like to talk a little bit about an example in higher dimensions. So this was studied in the literature in 1996, and they got some results. So the idea is you have this set B, which is a set of complex numbers, and would be positive numbers, and could be any integer, positive or negative. The analogy of the thetas I had before, of 1 over x plus m, is 1 over z plus b. So z is a complex number. Now my domain is a set of complex numbers that if you switch over to xy coordinates, they're in a circle of center a half 0. I look at a space of real-valued continuous functions, and I define this map, which looks pretty much like the map I had in the case of a real line, the derivative of this theta to the s power times this v. Okay, so there are two differences. One, I'm in two dimensions because I'm doing with complex variables. And second is, I'm not going to restrict this B to be a finite set. So I'm going to allow it to be infinite. Okay, so again, there's some invariant set whose Hausdorff dimension I want to compute. And what is that invariant set? Well, if you give me a set of these B's, then I can compose all these thetas, and I can get some limit point, b pi of omega. Omega is just a function of the B's. It doesn't depend on the Z. I can define my limit set. The invariant set is the set of all these limit points, and I can show that that set is exactly what I get if I take the union of all the theta b of k's. And the problem, again, is to find the Hausdorff dimension. As I've said, there's two issues here. One is, well, how are you going to work with an infinite set of B's? But it turns out that if you look at the series, as long as S is bigger than 1, it converges, so I can deal with the tail separately. What's the background? Well, it's the same thing. There's some unique eigenfunction. Lambda is positive, lambda is the spectral radius, and that's the definition. I should say one more thing, I guess I didn't write on the slide. The reason you can do this is the same reason the power method works, is that if you look at the spectral radius, it's the maximum eigenvalue, everything else is smaller size. So there's a separation that makes this work. So basically, I'm computing, let's say, the eigenvalue by some variation of the power method or whatever, and I don't have to worry about it because I know I have this separation. Okay, same thing. I get the Hausdorff dimension. I have to find the spectral radius equal to 1. So then what are my key estimates, which are the analogs of the one-dimensional? Well, now I'm in 2D. I need second derivatives. Turns out I don't have to worry about the mixed derivative. I get upper and lower bounds on the ratios for the pure second derivatives. I have a similar relationship between 2 points. That's what I need. So what do? Well, the first thing I say is, I can, if I take z bar, it's the same thing as z, so I can only work in the upper half plane. So I have a semicircle, and I just do something very simple. I just take a mesh of squares of side h, and I cover my domain. So in this problem, there's no boundary conditions or anything. So I cover it with that. So I get a mesh domain. Okay, if I'm on unit squares, then I can approximate by piecewise bilinear function. Why those are good is the same reason that the linears are good. If you have a bilinear function, I guess I'll write out the formula, and the bilinear function is non-negative at the 4 corners, it's non-negative everywhere because the basis functions are non-negative. Of course, I have to get this to a finite set, so I have to bound everything that's for which the b's are bigger than r. Again, I want to find these matrices that satisfy this property. Okay, the first thing is, if you have something like this and you look at the b's that are bigger than r, you can see from this theta plus b, it's getting some constant. I can bound the whole thing by just the point at 0. And the constant goes to 0 rapidly, well, it depends on s, as r goes to infinity. So here's a few computations with an r and an s, and you can see these numbers are fairly small. But it shows you how many turns you need to take, so this complicates the computation. Okay, so I remind you, what is the bilinear approximation? There it is on the bottom. You see it involves the 4 corners. You see the basis functions are all non-negative. They're just bilinear functions. So it has this key positivity property. Okay, so I have my upper bounds. I have my inequality. I plug all this into the error estimate for bilinear functions, which involve these pure second derivatives. And the whole thing, just like in the one-dimensional case, can be bounded by all things that are given explicitly, again, times the interpolant. And again, I've used the fact that on a square, how far could any point in the square be from any of its vertices? So square root of 2h. Okay, so I use all these bounds, and I can bound the error, again, in terms of just the interpolant itself. So I define these error functions, just like I did in the one-dimensional case, and what's the upshot? The upshot is I can look at the eigenfunction I'm interested in at theta b of the interpolation points, and that is bounded above below by the interpolant at those guys within some small error of order h squared. And what good is that? That allows me to define upper and lower matrices. So again, I look at the eigenvalue-eigenvector equation. I get that formula. I replace v at theta b by the error thing in VSI. Of course, I have this extra term. I do the same thing on the lowered bound. And then I use these formulas to define my matrix. So again, I take my vector corresponding to the eigenfunction of that interpolant. I define the matrices, and that gives me the elements of the matrices. The key thing is these matrices have non-negative entries, at least for h sufficiently small. That's why I did bilinear functions. Okay, I have the same setup. I know that the spectral radius times ws of k is bounded above and below by these ASWS kth component. I have my limit that says if this w, which is the interpolant of the eigenfunction, is strictly positive, and that's what the theorem says. It says the eigenfunction corresponding to the spectral radius is strictly positive, then the way I've constructed the matrices guarantees me the relationship of the spectral radius. So I do the same thing. So if I have my S star, if I can find some guy that's less than 1, then I can get an upper bound or a lower bound on the S star that I'm looking for. I choose a sufficiently fine mesh, large enough R, and I can get rigorous upper and lower bounds. Okay, same deal. I have this nonlinear approximation. I have to solve R of AS is 1. Of course, it depends on S. So given an S, I know how to compute the eigenvalues. I have to solve the nonlinear equation in S. This logarithm gives me a convex function. So I have a very simple nonlinear equation to solve. And then I do some computations, much more complicated. I'm not getting 15 decimal places here because I didn't take a very small h, and I took a big R because basically my computer's not too fast, and there's a limited amount of time I want to sit around waiting. So, but you get, 3 decimal places of accuracy without much work. Okay, so I'm going to summarize here. What did I do? Well, I wanted to find explicit upper and lower bounds on the Hausdorff dimension for certain problems. The key idea is that the Hausdorff dimension is related to a spectral radius of one of these nonlinear operators. Okay, now we're in the realm of things we all understand. We have these operators, we know how to deal with them. Unlike in PD, which I usually work at, you can actually get explicit upper and lower bounds on the derivatives of the eigenfunction corresponding to the maximum eigenvalue. Not usually the case. Things you can do is if you use linear or bilinear functions, this positivity constraint is enforced only by requiring it mesh points. So that's in some sense what makes this a compatible discretization. You have a positive operator and you get these positive matrices. And then the scheme I'm picking, how do I get my approximate eigenvalue eigenfunction thing? Well, everything hinges on that I know stuff at mesh points. So essentially taking the operator and doing a collocation scheme. If you use the Galerkin scheme, you might lose some of this positivity unless you can use piecewise constants, that would be okay. So that allows you to get a very direct relationship between the operator you started with and the approximate operator. So that's kind of the summary of what we did in these cases. We're trying to extend this theory so we can do higher order piecewise polynomials. It's because these codes are more complicated, it is more complicated, and I will stop here and see if anybody has any questions.
Well, we have lots of time for questions. So, look.
So you computed these dimensions out to 12, 15 decimal places. How many decimal places do they want? What's useful?
Well, you know, that is a funny thing. So there are guys out there who want to show you how great their method is. So they have computed E12 to 100 decimal places. Now, I can't think of any reason why they would want to know that. They just want to show you how great the method was, okay? In principle, I could compute this as, you know, I have done this. So I have multiple precision version of MATLAB, and I computed these things. So maybe when we write this other paper, I'll show, yes, we could get 50 decimal places. I don't know. I mean, I couldn't find any example where they needed to know that. And we have a guy who's a number theorist, and he did some problem. He was happy with 3 decimal places. So for the thing he wanted to do. So 100, I don't know. But I would say that the difference of what we did is there's a lot of people who've worked on this over many years. They've done computations. I would say the new thing we did that nobody had done is give these explicit upper and lower bounds. They did the computation. They said, here's what we got. We said, yeah, well, is it any good? And so we did that. And since then, other people have now seen, oh, that would be a good thing to do, and they have now taken that up. So I would say that's the new part of the theory. Now, there's a lot of other problems related to this.
But what is the reason why people from the beginning were interested in this problem? Were it because of pure math questions?
Oh yeah, it comes up, well, it comes up, I guess people are interested in number theory. I had some slide there, I forget what it was, some called Zorinda's conjecture. And actually, there's another application of numerical analysis. It turns out that when you do a Monte Carlo method, there's a rate of convergence of the Monte Carlo. I think when you take the number of points, maybe it's the square root of the number of points, but something like that. It turns out if you choose these points more judiciously, so you get a quasi-Monte Carlo method, you can increase the rate of convergence. And the points you want to choose, they're somehow related to this whole business of Hausdorff dimension. So it actually shows up in an application that might be interested in it. But there's many others, and that's not my field, but there's a lot of people who do it.
Another question. How did you get interested in this problem?
My colleague Roger Nussbaum. See, he's worked, he's a nonlinear functional analyst, he's worked on these mapping of cones, and he had an idea that you could make a numerical algorithm. But he's not a guy that's very computer literate. So, for example, wasn't that long ago, I taught him how to use email. So he wasn't going to write any of these programs, and I didn't quite appreciate the numerical analysis part, although he understood these theorems that I'm quoting about the theoretical background, many are due to him. So he understood the relationship of this Perron-Frobenius operator and what you could do with it. So I would say those are the ideas, and since we're friends, he came, well, I remember we used to be friends, came to me and said, maybe you would like to participate in this project, and so we started working. Because otherwise, if you would have said to me, yeah, I think you're going to be doing numerical approximation of Hausdorff dimension.
Because you started saying that your background is in finite elements, right?
That's right.
So it's very surprising that you are doing something which is
Well,
not
don't
apparently...
you see any finite elements? Piecewise linear, piecewise linear approximation, piecewise bilinear approximation. You know, error estimates, compatible discretizations. We're trying to do higher order. we have to use, it's not even exactly these points.
Yeah, well, I see that you have brought your background into the project, but the
That's right.
original, yeah.
But I agree with you, it was a stretch.
Stretch,
It was a
yeah.
stretch.
Okay, any other questions?
So when you do higher order, you have to deal with this sort of non-cone, or sort of generalized cone condition.
Yeah,
Is
So
that
you have
described
to-
somewhere?
so you have to get a different kind of a cone. And there are kind of, I think, my colleague Roger had used one other kind of cone. And it turned out that we could, that's totally simple, but you could use that cone and show that on the finite dimensional level. So basically, you have some cone that you define, and you show your mapping takes that cone into a smaller cone of the same type, and then you get this theory. Goes through basically in the same
So
way.
you don't need to.
So you have, the definition is not, completely trivial what those cones are, and the proofs that the thing maps these cones into itself, that again is not a trivial fact. But I think it's interesting because most people would have thought, me included, wow, I use higher polynomials, you don't have positivity, that's it, you're done. So we're going to call this paper something like hidden positivity, because it is there in a way that you can use.
I see. This is something you're writing.
We're in progress. That's my story of my life. I'm in progress with Ragnar, I'm in progress with Roger, and I just got to keep, staying alive to finish these papers. That's my goal.
Any other question? If not, let's thank again. We have plenty of time before the next stop. At 5 minutes past, you have to be here. So use this time wisely to get a coffee or to go to the toilet. And at 3 o'clock, I want you back here, please.
12 minutes, use them wisely.
Thank you very much. I think that, what did we do? We stopped recording and.